Hello everyone, welcome back to LeetCode Daily Live where I do the daily question raw and uncut. So we have a hard today, it's called maximum number of tasks you can assign. So let's see what arguments we have first. So we have an array of int task, also an array of int of workers, and then we have two numbers called pews and strings. So let's look at the bounds. Right, so all of them could be 50k length. And the numbers, so the numbers are either 0, so any int, but it can't be negative, basically. And then we have pews, so the number of pews, is bounded by the number of workers, it looks like. Yeah, so let's see what the question wants. So yeah, you have n tasks, n workers. So each task has a strength requirement stored in the integer array task. So the ith task requiring task I strength to complete. Right, and then the strength of each worker. Okay, so the worker also have like some strength, I guess. Yeah, so the jth worker having workers j strength. And each worker can only assign to a single task and must have a strength greater than or equal to the task strength requirement. So, okay, so that means like for the worker to do the task, and we can only do one task, it has to have a strength greater than the task. So it sounds like some allocation problem, which reminds me of MaxFlow, but surely like LeetCode, we don't have to do MaxFlow because it takes quite a long time to just like to write out the MaxFlow stuff. So yeah, let's just keep reading for now. So you also have pews, which will increase a worker's strength by strength. So okay, so you have pews amount of pews, and each of them can increase the worker's strength by like the variable strength. You can decide which workers receive the magical pews, but you can only give each worker at most one magical pew. So given the zero index integer arrays, yeah, actually like this pew thing really reminds me of a MaxFlow problem that I did before. It's something like each hero can has to like defeat like one monster, but then you can give a magic pew to like it's like a magic potion to like one hero, and you want to find out the maximum amount of monsters you can defeat, something like that. So here, we actually like the question is very similar, but then I think like the bounds might be a bit too large. Yeah, cause like for MaxFlow, so basically like for MaxFlow you want to form the MaxFlow graph, right? But like in this case, we will have to connect every worker with every task allocation, so that will make like 50k squared amount of edges, which is definitely way too much. So yeah, it can't be MaxFlow, I think. Yeah, let's just look at some example first. So for example 1, we have task 3, 2, and 1, and then we have we have these workers. So yeah, so it makes sense to give the pew to the zero, like to the worker with 0 strength, because like he'll be able to do 1, and then like the other 2 can like do the other 2 tasks. So that's why the output is 3. Okay. So for this one, we have 1 pew. Yeah, so we can only give 1 pew to like one person. Yeah, and then it'll be able to do either 5 or 4, but like no other task could be done. So that's why it's 1. So let's look at the third example. So we have these stuff. Yeah, so the answer says it is 2. This one is not too obvious why. Well, I guess like first of all, a 10 can definitely do this task. Okay, and then you can give appeal to like one of the workers, but each worker can only get one pill, I'm pretty sure. Yeah, you can only give each worker at most one magical pill. Yeah, so that means like none of them can actually do the task that requires like a strength of 30, because none of them can take two pills. So so that's why it is 2. Honestly, like whenever you see some like allocation kind of problem, like max flow most likely works, but like again, there isn't an obvious answer here. Let's see what we can do though. So some observations. So like I guess like when you're looking at these examples, you have like you definitely want to like somewhat sort the task and workers. And so if the worker with the like largest strength can do the task, you want to get rid of it first, cause like it makes sense to like if you don't have to give a pill to a worker, but it can still solve the most complex task, it would be greedily the best, I think. So that's the first observation. What about something like, so I guess like in this case, well, this is like better than this, so we can like get this. This is better than this case. So again, like we can just pop them, and then here, we can see like whether having the pill can like solve that problem, or if there are more problems, like what we can do afterwards. I guess these are like quite generic cases though. Let's look at example 3 actually. So we have tasks 10, 15, and 30, and then we have workers 0, 10, 10, 10, 10. So it definitely makes sense to like go from the largest, I think. So if we have 10 here, so like because this is the largest, right? If this can't solve the task if this can't solve the largest task, then we'll just go to the next one. But I guess like there are 2 potential like ways we can sweep like the task. So either we want to go from the bottom, or want to go like, well, either we're going to go largest to smallest, or smallest to largest. But I guess like smallest to largest doesn't really make sense, because it is not optimal to like to get the worker with the largest strength to solve the smallest. So I guess like the only real option is like going that way. So largest to smallest. So if you give a pill to this worker, it can't solve that task. That means like none of them can solve that task. So we'll look at the next one, and then like for this we can give a pill, but then we also have an option to like either give a pill or not give a pill. Like, is it always better to give a pill if that person can solve? Or is it better to leave it? I guess like there are some cases where like you give the strongest worker the pill, but then it just makes like all the other ones like not fireable. So that's like one counter example for like always giving the pill. Can we do like a DP though? I don't think we can. So for DP, we'll have the state like number of pills left, and then we will have like the worker. But then again, like this will be like n squared, right? Which is too large, so we can't do that. But it's also not max flow. So it's not max flow, it's not DP. Can we turn this into a decision problem maybe? Because like whenever you see something like return the maximum number and you can't really see a way forward, it's always good to try turning it into a decision problem. So it doesn't make sense to do a decision problem here. So that would be turning the problem from finding the maximum to whether we can solve k task. And if we can solve k task, we can solve k minus 1, right? Yeah, actually, I might be cooking here. Let me think. Yeah, so if you want to see if you can solve k task, it makes sense to look at the strongest k workers and look at the k easiest task, I think. Yeah, I think that'll work. So yeah, I guess like none of these examples are that good, but like basically if we sort it, so let's say we have like some task here and then we have like some workers and we have 2 pills, let's say, of strength 1. So if we want to see whether we can solve k task, so let's say k is equal to 2. Yeah, how do we want to assign it? Actually, would this still fall into the problems from before? Oh, actually, if we do this, well, actually, like the reason why I picked the strongest k workers and the weakest and the easiest task is that like by exchange lemma, like you can switch the task and like and choosing the weaker task and the stronger workers will be optimal, right? So yeah, actually now that we have a set number of workers and a set number of tasks, I think it'll make it a simple greedy problem, right? Yeah, so obviously like if k is equal to 2, we can just solve this and then solve that. So that's very straightforward. But what if we have like let's turn it into like 2 and 2 maybe. What if we have like 4? So because now, like for the problem before, we don't know whether we want to solve the task or not, right? And that creates a lot more states. But now we are forced to solve the task. So when we look at the best worker and compare with the hardest task, we need to make sure that this worker can solve that task. Because if the strongest worker can't solve the task, no one else can, right? Yeah, so that means like for that k it wouldn't work. So yeah, actually like in this case we'll be forced to like give up a pill and then it will work, and then we look at this, so that will also work, and then that'll work and that'll work. But then if we have 5, well, even if we have like 3 here, let's say we have like 1. Yeah, so like 3, like the worker with 3 strength will have to solve the task with 4 after taking a pill. 2 is solve 3 after taking a pill. But then when we get here, we don't have any more pills. Yeah, actually, I think this will work. So basically, we turn it into a decision problem, and then we can just do a simple greedy. Yeah, actually, yeah, that'll work. Unless it doesn't, but I'm pretty confident it'll work actually. So let's start coding, I guess. So first of all, we want to sort the task, and then we want to sort the workers. We want to sort the workers from strongest to weakest, I think. So we just do sort and then reverse. We'll just do it here. I think it's reversed equals true. Let's just make sure the syntax is right here. I think it's reversed then. Yeah, okay. So again, we need binary search, so we need a left and right bound. So in the worst case, we cannot solve any task. And in the best case, we solve all the tasks. So it will be a length of tasks. And now while do I remember my binary template? Let's see. Yeah, so the reason I use an answer here is because like in binary search, sometimes you're like looking for the exact element, sometimes it's like between some elements, sometimes it's like on the edge, like on the two edges. The way I do it makes it so that it accounts for all the edge cases. Yeah, so it's just a bit nicer, I guess. So we just do let's just call it valid. Terrible name, but so we have K, and then and then it should return a boolean, I think. So we have the function here, and then if valid, so if valid, so that means like if we can solve m task, then what do we want to do? If we know we can solve it, we want to look on the right half. So we'll turn our left bound up there, and then we'll also set our answer to m, because like this is a valid answer, right? So at the end, answer is going to take in the largest answer that it can solve, or something like that. Otherwise, so if m is like if m task is not like if the workers can't solve m task, we will have to look on the left hand side. So that's why we'll set the bound there, and then when they overlap, so when L is equal to R, M is going to be like equal to L, and then it will check that, and yeah, and then like either of the bounds will move across to the other side, and then it will pop out. So yes, my template is correct, I think. So in terms of here, we want to do like pills left. We'll set it as pills. So now for I in range, K. So remember the task, we have sorted from smallest to largest. For workers, we have sorted it from largest to smallest. So we can actually like use the same index for the correct positions. So so if task I, wait, actually, oh, we actually can't do that, because we want the, yeah, okay, we can't use the same index, because like we want our strongest worker to solve the hardest task, right? So actually we will need to do if we have K task, the task we will be looking for is k minus I minus 1, I think. And then the workers will, for the workers, we will be looking at the strongest one. So that part is fine. So if the task, if the worker can solve it without any problem, then we can continue. But otherwise, if we have no pills left, so when we get here, that means our current worker can't solve the task without pills, or even like with pills it can't solve. But like first of all, we will check whether we have any pills left. So if we don't have any left, then the worker can't solve the problem, and hence we can't solve K task. Otherwise, we are going to take a pill, like let the worker take a pill, and then we'll check this thing again. Yeah, and then like we'll add the strength here. Yeah, strength. So if we can do that, like we can continue. But actually, we're after the other case. So if after taking the pill, the task is still too hard to be solved, we want to return false here. But if all the workers can solve their corresponding task, it will work. Yeah, I'm still looking here. Is this correct? Cannot access. Oh, pills left. Yeah, I think that should be correct. Oh. Yeah, what is this case here? So our output is 2. Yeah, actually one thing I want to check is whether there's an off by 1 error here. So if we have K task, we want to look from K minus 1 all the way to task 0. Actually, let's print out task and worker so we know they are behaving as we want. Yeah, so those are the tasks. These are the workers. So let's see. Yeah, let's see what the issue is. So for my answer, I got 2 here, but actually it suggests that it should be 3. So these are the tasks, and then these are the workers. So first of all, this worker is going to solve this task. Does it have to take the pill? Yeah, we have 1 pill, so yes, it will have to take the pill. And then that solves this, and but we only have 1 pill. So how can 4 solve the task of 5? Unless I'm missing something. Like, can we split the pill? I'm pretty sure not, right? Wait, am I misunderstanding something? So each worker can only be assigned a single task. Oh, can we? Right, okay, I see the issue with my algorithm. So actually in this case, 6 and 6 can solve 5 and 5, right? But then, so before I was assigning like 6 has to solve 8. So yeah, actually, we want to give the pill. So like for this task, we want to give the pill to the weakest worker. That after taking the pill can like solve the problem, I think. So we need to change this part here. That means but is it still true that if our best worker can solve the most complex task, we should still like pop that? Yeah, actually, I don't think that's true anymore. Cause like, let's say you have a really good worker, and then you have like a weaker. Yeah, I was thinking like a 6 6, and then you have like 8 and 4. I think it's still true. So maybe 6 and 6 is not that good of a choice. Yeah, but something like this. So like, wait. Actually, if the worker is good enough to solve the most complex task, I think we still want to. What if we do it the other way, like from easiest task to hardest task? What if we do it that way? I don't think it actually makes a difference, or does it? Oh, you guys can't see that. Yeah, so that's the thing I was drawing out. Yeah, so we have like 3. Yeah, I think like we need some priority queue or something to basically like add the workers available and stuff. Yeah, so but I still think like if there's a worker that can solve any problem, because each worker has to solve a problem, right? Like in our decision problem, it is still the best to like just solve that problem. But then like for example, if our pew is like equal to 5 and we have like one pew here, we actually don't want to give the pew to 6. We want to give the pew to 3 so that it can solve the task for 8. And then like 6 can solve for 4. Yeah, so actually, yeah, I do think we want some sort of queue so we can like maybe a sorted list or something like that. But basically, like we should keep adding the workers until we see a worker that after taking the pill is still not strong enough. I think like that's the only change we have to make. How do you want to go about this though? Yeah, so obviously we have to change this part here. But I think like actually let's get this back because like most of these are still correct. So yeah, I guess it's like when we get here. Let's have like a. Do you want a priority queue or? Yeah, so we have a. So I guess we have like worker index. And then we have a task index. So worker index should go from 0, right? And then task index should go from k minus 1. Yeah, so what should we do here? Yeah, actually, what is a nice way of coding this out? Is there no nice way to like select the weakest worker or something? Hmm. Yeah, because like after we choose that work, I guess another way to do it is like we bisect our workers array, uh, which allows us to find the worker with the weakest task, and then we can like we can use that worker instead, and then like we just don't increment for like our index here. I think that might work. So we have a worker set. Yeah, but that means like we do have to redo this whole part. So so I guess like while worker index is smaller than k, and then like make sure that we remember to increment. So if so the task index is also, maybe we should use the task index actually, because the task index is the thing that always goes down. So while it is larger, so task index, like because we are looking at each task, right? It's just that like for some tasks that our best worker can't solve, we want to look for the weakest worker that can take the pill and solve it. So that's the only change, I guess, that we have. So if worker is if worker index, so the same thing happens if our strongest worker can solve the hardest task that we are looking at right now. So we just do that. And then else if, so after we pass this, if our strongest worker, after taking the pill, well actually like if the strongest worker can't solve the task and we don't have any pills left, we want to return false. And also I guess we can do else here. So like in our logic here, we'll work out whether after taking the pill, the worker can. Now actually, let's have that case here as well. So that means, so if plus strength is still less than the task that we're trying to solve at the moment. So now we know that some worker can take the pill and solve it. So we want to so we have a bunch of workers. And we want to bisect, I guess. Yeah, but if we're using this set here, it is going to yeah, if we're using the set here, so let's say like we have two tasks that falls into like the same worker or something. Yeah, I guess like a not too nice solution is like we can keep looking down until, wait, actually, yeah, so after we use bisect right. So let's say we have like a bunch of workers here. So the problem I'm worried about is like if our bisect right lands here and we have used this worker already, then we have to like look at the next one, right? So technically that would make it n squared. I'm sure there are like some nicer ways of doing it, but I don't think in our case. Yeah, I'm just gonna guess that there isn't a case where you look at all of them. But like a nicer way is like you use a priority queue and then like yeah, actually I'm not even sure if that's actually a nicer way. Oh wait a second. There's a thing I was always kind of worried about is that if we add the whole array in here, it will be too slow. But actually, no, we can do on here, so we can use sorted list, and actually, yeah, that will make the whole thing a lot easier. So and a lot cleaner as well. So let's do that. So from collections, import sorted list. So yeah, so we don't need the set anymore. So we have the worker sorted list. So we want the sorted list of the workers up to k. So that'll get the k strongest workers. Yeah, and then here yeah, so what we can do is we can just do bisect right for our current worker, I guess. So task index yeah, we use the sorted list here. So worker sorted list, and then wait, I think we want to add one. Yeah, because like we are sorted from strongest to weakest. So bisect right minus strength. So that will give us the worker that can just solve the problem, I think. But I have to do a -1 here. So index is this, and we want to remove the I guess like we can do something like remove. So we want to remove the worker with this index here. And then we don't want to actually shift the index. Even if it is the strongest worker, it will get removed, and then like everything else would move down one. So that will still work, I think. Can I import sorted list? Oh, because it's from sorted containers. Oops. Does this work? Now this part doesn't work. Let's see what the issue is. So expected is 3. So the way I do it, so this can solve this, this can solve this. This should be able to solve this though. I'm probably just I probably just have some logic messed up here, I think. So it shouldn't fall into any of the cases here, and because like we can technically solve everything, so let's see, where does it run into it? Oh, oops, I did the same number. And then we can print W index, T index, and also K. I'm pretty sure it fell into this case here, which is a bit unfortunate. Yeah, so W index is 0. Wait, actually, let's not use W index. I think that'll only mess things up, like in the future. We'll just remove the worker. So we'll just remove the worker, the best worker in this case. Yeah, so we'll run this again. W index. Yeah, so we'll do this instead to like get the strongest worker instead of like using a worker index to keep track. Yeah, so here as well, we're checking whether our strongest worker with the pure can solve the task, right? I need to get rid of this as well. Oops. There any more worker index? I don't think so. Invalid syntax. So the T index is 2. So we are looking at the last task, which is. Wait, are we looking at the last task? No, we are not looking at the last task. So T index is 2. That means it hasn't even gotten here yet. We have a 3 here. Yeah, so it does make sense, like, this is the case. I guess, like, we'll print out the worker we are looking at and also the task we are dealing with to get a better understanding of why this is happening. Our worker is... Oh, I see now. We're not actually getting the strongest worker. We're getting the weakest worker right now. So that was the issue. Because like, I think sorted list, we can do reverse is true. I think. I'm actually not sure whether we can do this. So we still want to sort it from strongest to largest. Yeah, it doesn't seem like we have that option though, which is quite sad. So that means we have to I guess like if we do -1, we'll get the largest. And then we want to also need to like sort this issue out as well. So we want to do bisect left, I think. So because like we are mirrored on the other way now. So instead of bisect right, we'll do bisect left. We are still looking for the first person with this strength here. Yeah, we would do +1 here. Well, actually, do we want to do plus? No, I don't think we want this anymore. Now these are not working. What is the issue here? What is the issue? Yeah, so the reason we don't need +1 here is because like bisect finds the index this number will be inserted into. And the next number would be either this number or larger, right? So that's why like that should be correct. Yeah, I don't know what else is wrong here. Is it like when we... So what was my answer? My answer is 2 here for some reason. Yeah, I guess another thing we have to check is like... yeah, we should do like number of workers here as well. Because we can only like every worker can only do one task. So we can only solve the number of workers amount of task. But why is it 2 here? So T index So that would be 1. It would be this task. Oh, I forgot to get rid of a pill. So pills left. Uh-oh. Which case? Oh, this case. So which is the thing that seems like it's this one. So we still have task. Huh. I guess we can do this to like find out which problem. Like where's the problem? It does seem like it is this thing. So what is the task index here? Because like after we fix this, that shouldn't happen. Now it is this thing here. Why is that? I'm kind of confused now. Wait, so if we print -1, I'm just worried that like all the workers have been removed. Okay, so it is the task thing being wrong. So it should be K here. Yeah, I think like for the case that's not working. So let's print K here. So for the case that's not working, I think K is equal to 3. Or am I wrong? K is equal to 4? Huh? Oh, we have like... yeah, okay. So many edge cases here. Yeah, so if we don't have that many tasks, we can't actually like solve that anyway. So that's why we need that. Does it finally work? I don't even know if it does, but let's see. Hopefully it doesn't time out. Okay, it finally works. Yeah, this problem... Honestly, this problem is a well-deserved hard. And also, I am not the best today. I ran into so many edge cases. Maybe if I get rid of this, it'll be faster. But yeah, I think like you have to find out that it is a decision problem, and then yeah, also like the reason why it is so slow is because I'm using sorted list. I'm pretty sure there are like nicer ways like to do it, like maybe by using like a priority queue or something like that. But yeah, I need more stuff. No, I guess it's just me, like running into a lot of edge cases and like having to change my algo a few times. But yeah, I think this question is pretty good. I like this question. And thanks for watching, and I'll see you tomorrow. Bye.